Our world runs on all these invisible rules. They're humming away in the math that calculates your paycheck and in the code that powers your phone. And it might not seem like it, but a fundamental logic connects them all. So today, we're going to pull back the curtain and uncover that hidden system, starting with a pretty simple question.
Okay, so at first glance, right, these two things couldn't be more different. One's about your money, the other is about lines of code. But the link between them, it actually points to something really fundamental about how we structure our world. And it all boils down to a set of predictable rules.
And there you have it. They're both driven by these really precise, predictable principles. One set of rules governs how numbers relate to each other, while a whole other set governs truth and ideas. So let's kick things off with the numbers. All right, first up, let's talk about something we all do without even thinking about it: comparing things. This is the world of proportions. And trust me, you're using this kind of logic all the time, whether you're in the kitchen, behind the wheel, or just trying to figure out if you're getting a good deal. See, a proportion isn't just a couple of numbers sitting next to each other. Nope. It's a relationship. It tells a story about what happens to one thing when another thing changes. And as you're about to see, that story can go in two totally different directions. So this relationship basically forks in the road. On one side, you've got direct proportion. When one thing goes up, the other goes right up with it. You work more hours, you earn more money. Super simple, right? Then you've got its opposite, inverse proportion. When one thing goes up, the other goes down. The faster you drive, the less time your trip takes. They move in opposite directions. This is like the perfect example. That core ratio, $15 for 1 hour, that's our constant. It's locked in. Work 2 hours, you get $30. Work 10 hours, you get $150. That 1 to 15 relationship is always there. It's this super predictable, direct link. Okay, so inverse proportion might look a little tricky at first, but the logic behind it is actually pretty straightforward. The whole game is to find this one constant number that ties the two things together. Here, it's speed and time. By multiplying our starting point, 60 miles per hour times 3 hours, we get our constant, 180. And once you have that number, you can solve for pretty much anything. So if the trip suddenly takes 4 hours, all we do is take our constant, 180, divide by 4, and boom, our new speed is 45 miles per hour. The relationship is still perfectly consistent, just in reverse. Okay, so we've got these nice, clean rules for how numbers relate to each other. That makes sense. But what about ideas? How in the world do you build a system of rules for things that aren't numbers, like statements and arguments? This is where we make a huge shift from the world of quantity to the world of quality, from asking how much to something way more fundamental. Is this true? And that right there is the big question. To even start building rules for truth, we're going to need a whole new kind of tool. We need a system that can handle statements, not just figures. And that system? It's called propositional logic. All right, this is the absolute core concept. I want you to think of a proposition as like the atom of logic. It's one solid declarative statement that has to be either true or false. There's no in between, no maybe, no kinda. In this world, everything is black or white. And telling them apart is actually pretty easy. The sun rises in the east, that's a proposition. Why? Because you can check it. It's true. B is a vowel, also a proposition. It just happens to be false. But if I ask, what time is it? Or tell you, go out and play, you can't say that question is true or false, right? It just is. It doesn't have a truth value, so it's not a proposition. Okay, so a single proposition is cool and all, but the real magic, the real power, happens when we start chaining them together. And to do that, we need something like a grammar for logic, a set of operators, or what they call connectives, that let us build really complex ideas out of these simple true or false building blocks. First up, we've got the simplest one of all, not. It's basically just a flip switch. If the statement, it is raining, is true, then adding not makes it is not raining false. Easy. All right, now let's use and to connect two ideas. And, well, and is the strict one. For the whole sentence, today is Friday and it is raining. To be true, you need both things to be true. No exceptions. If it's Friday but it's sunny, the whole thing collapses. It's false. Or, on the other hand, is way more chill. For the statement, today is Friday or it is raining, to be true, you just need at least one of the parts to be true. It could be a rainy Friday, a rainy Tuesday, or a sunny Friday, all true. The only way it's false is if it's, say, a sunny Thursday, when both parts are totally false. Now, this next one, if, then, is a little different. It's all about making a promise. If I say, if it is Friday, then it is raining, I'm only making a promise about Fridays. So the only way you can call me a liar, the only way to break that promise, is if it is Friday and it's not raining. Any other day of the week? Doesn't matter if it's raining or not. My promise about Friday is still safe.
And last but not least, we've got the biconditional. People sometimes call it if and only if, or IFF for short. The easiest way to think about this is like a logical equal sign. It's basically saying these two statements are locked together. They rise and fall together. The whole thing is true only if they match. Either both are true or both are false.
Okay, I get it. Trying to juggle all these rules in your head can feel like a lot. But luckily, there's this incredible tool for visualizing every single possibility. And don't think of it as some boring chart. It's the ultimate cheat sheet for logic. It's called a truth table. So what a truth table does is it just lays everything out for us. It gives you this perfect bird's eye view of every single outcome. We can map out every combination of true and false for our simple statements and see exactly how it all plays out. No more guessing.
So check this out. Here's the truth table for and. Look at that. Out of 4 possible combos, there is only one single row where the result is true. And that's the row where P and Q are both true. See? That's just how strict the and operator is.
Okay, now let's immediately compare that to the table for or. See the difference? It's huge. The result is true in 3 out of the 4 cases. There's only one way for P or Q to be false, and that's in the very last row where both of them are false. It's practically the mirror image of the and table.
So at this point, you might be wondering, okay, this is kind of cool, but is it actually useful? And the answer is a huge, resounding yes. This stuff isn't just a fun mental puzzle. It's the hidden engine running so much of our modern world. I mean, this isn't just theory. This is literally the architecture of our digital world. That if/then logic we just talked about, that is the absolute backbone of pretty much all computer programming. Those and/or operators are what power every database search you've ever done. This is how AI algorithms make decisions. It's how lawyers build airtight arguments. It is absolutely everywhere, humming away just beneath the surface. So, from simple, everyday ratios to the deep grammar of truth itself, we've seen how our world runs on these profound but totally understandable rules. What we've explored today is really just the tip of the iceberg. Which brings me to the final question I want to leave you with. What other invisible rules of reason are out there quietly shaping our reality every single day?